In lecture 26, we started to talk about holes. When we have a hole in a function, how do we end up saying that we have a hole? And then we started to talk in terms of limits of how can we characterize holes in a function. But in this particular lesson of today, we will be talking about asymptotes. Our main goal would be based on vertical asymptotes, and maybe at a later stage when we are actually dealing with limits at infinity, that's when we'll be starting by talking about horizontal asymptotes. For now, we are only talking about vertical asymptotes. Just a quick recap. We said that if, let's say, the question is saying evaluate a limit. Let me fix this a little bit. So suppose I'm saying evaluate a limit as x approaches some number a of f of x, and we said that if, let's say, you end up having, if I take this a here and I plug it in the value of x, I find out that I have my f of a is equal to some 0 over 0. And then when I'm factorizing this f of x and then cancelling out the common factor, I end up getting a number. Or when I realize that I still have 0 over 0, and when I rationalize this fraction and cancelling out the common factor, I get a number. We said that we definitely know what is happening with that function around point A, and we said that, of course, what will actually happen around that point, we actually gonna end up having a nice function that is going to be smooth like this. But at this point here, when x is equal to a, we know that we must have a hole. That's what we're talking about, that if you have a 0 over 0, you must know that at that point you must have a hole. If now I have this nice thing, then I know how to deal with it. The limit, to evaluate a limit. That one thing that I can do, I can factorize, cancel out the common factor, and then plug in. Or I can rationalize, and then after rationalizing, I know that I will actually end up having a common factor that needs to be cancelled. So today what I want us to look at is this. It's actually basically 3 scenarios. Okay, let me say 4. But in matter of fact, there are actually 3. Let me just draw these curves and then we analyze. Yes, now I have these Cartesian planes, and then I have drawn an asymptote at x is equal to a vertical asymptote at x is equal to a vertical asymptote at x is equal to a. Now, what I want us to notice here is that if you have an asymptote at value a, then if the function is defined on both sides of this asymptote, the function can either be getting closer and closer and closer and closer to that asymptote, and it keeps going closer all the way, but it never gonna touch that. And also on the other side, we can either end up having this function getting closer and closer, but it's never gonna touch it. It's gonna keep continuing all the way up, and here is still gonna continue all the way up. Or the function will be getting closer and closer and closer on the left of a, and getting closer and closer, but it's never gonna get to a, but it's gonna keep going all the way down. And on the other side also is gonna get closer and closer. This one is not that looking good. So it can either get closer and closer and closer and closer and closer, but it's still going to continue. So basically what we are trying to see here is the behavior of a function around the asymptote. And also another case will be on one side the function is getting closer but still increasing unboundedly, so it's going all the way up, it keeps increasing, but on the other side it keeps coming down all the way down, but it's never going to touch the asymptotes. So we end up having these different scenarios, or this side it is going down and then this side is going up. So how do we say this is happening if you are given some function, right? For this particular case here, when both this is going all the way up and both this side and that side, all they are going all the way up, what we say here, we just say the limit as x approaches a of f of x is going all the way up to all the big positive numbers. So we say to positive infinity. So this limit of this, when you're evaluating it, you end up getting a positive infinity because all the values are actually going up. Essentially, to find out what is happening here or to evaluate, you pick a value so close to a such that if you are plugging it here, you get a positive value. That positive value is the one that will actually tell you that you are actually having this particular number here, or this particular solution, which is positive infinity. And to say that we're actually having this case around the asymptote, which at this value a, we just say that the limit as x approaches a of f of x is equal to negative infinity. Take note that all these, both this side, the function is going all the way down, and also this side, the function is going all the way down. So we say when we have a situation like this, that we actually have the limit is going to negative infinity. Or we can just say that this function f of s is decreasing unboundedly. So it's decreasing to negative, or to negative infinity as x approaches a. Or you can say that f of x is approaching negative infinity as x approaches a. The same thing here, f of x is going to positive infinity as x approaches a. Some other people prefer to say that f of x is approaching positive infinity as x approaches a. This way is another way of writing this, and it's actually easy for you to say this in words, because f of x, this arrow is saying approaches, so you can say f of x approaches positive infinity as x approaches a. The same thing here, you can say f of x is actually approaching negative infinity as x approaches a. Different way of saying the same thing, but you have to know all of them. Try and find different ways of actually saying the same thing, because if you have a function here, this function here is actually increasing, or is actually gaining positive and big numbers. So f of x is actually getting bigger and bigger as we're actually approaching a. So it's actually getting bigger and bigger. That's also another way of saying the same thing. This one here is saying f of x is actually, someone might say to you that this function actually is actually getting is going to big negative numbers as x approaches a. Different ways of saying the same thing. I'm not here to say that this one is better than the other, because some people criticize and say no, this is not big, it is something that is negative. It's getting bigger, but on the negative side, someone might defend and say like that. I just want you to know the terms when it comes to this. We'll do some examples at a later stage. Now, if you look into this particular case here, you can see that the function is going up. It's taking all the positive values as you are actually getting closer to a, but on the left of a. So on the left, or if you checked, I think we were doing lecture 27, we talked about one-sided limits. So in this particular case here, if you look at this limit as x approaches a, on the left, having the minus is saying on the left of a, if I were to pick a value just close to a, you'll find out that I will get a very big number of this actually f of x. In other words, I will get a positive infinity. But if I am looking at the limit as x approaches a on the right, so if I pick a value here and then plug it in the function, I will end up getting a very big negative number here of this function f of x. I will end up having a negative infinity. Because negative infinity, I mean positive infinity and negative infinity are different. This one is a very big negative number, this one a very big positive. Positive and negative are not the same. So we usually say when we have a situation like this, the limit does not exist. In this particular case, we have the limit as x approaches a of f of x. We say that it does not exist, or DNE. So that's what actually we mean by this. But now, if you look into this now, the main goal of actually explaining these legally things are not that important for now, but at a later stage they start to make a lot of sense, because the main goal of what we are doing here is actually to end up having a complete analysis of a function. In other words, if you are given a function, can you analyze it fully, get the critical values, get the domain of that function, get the range out of once you get the domain, what is actually happening close to the endpoints, if there are some endpoints in that particular domain, and then if you have some asymptotes, what is the behavior of the function along those particular points, and when is the function increasing, when is it decreasing, and when are you actually having saddle points, when are you actually having turning points, all those kind of things. That's the main end goal of this particular course. So if, let's say, now we are dealing with these asymptotes and we know that close to the asymptotes, what is supposed to happen? We either going to end up having both on both sides, the function is going up. Then we know that once we have the limit as x approaches a of that function is going to positive infinity, we know that at a we must have a vertical asymptotes. Or if we find out that the limit as x approaches a of f of x is negative infinity, we also know that there is a vertical asymptote at x is equal to a. And of course, in this case also, if you know that you have the limit as x approaches a of f of x is positive infinity when you're looking on the left, then you know that you have an asymptote there. And then when you're actually having this, you know that you have an asymptote. Now, let's go and look at the last particular case here. Suppose I have a function. Now, my function looks something like this. So it is increasing, and then it hits this point here. And then when you're going on the left here, I end up saying I have maybe a function that is actually increasing all the way, increasing, but it does not touch that value. So it keeps on increasing, but it does not touch this particular case here. Take note of this here. If, let's say, this value here, I said this value is L. So the limit as x approaches a on the left, right? If I were to pick a value so close here, I will end up hitting this function here, which is L. If this function here, let me say this is just my f of x, and when you're plotting it, you end up getting something weird like this. And then you have your f of x, and this f of x of yours now, you want to find the limit on the left. You will find out the limit on the left of this function is going to be L. But now, if, let's say, now I am actually looking at the limit as x approaches a on the right of this particular function here, you'll find out that if I were to pick a value so close, because this function is increasing unboundedly, it keeps increasing as it gets closer and closer to this. So when I'm picking a value so close here, I will get a very big number, because this will keep continuing to increase, but it's not going to touch this. So for this particular case, we'll end up having a positive infinity. Of course, looking at this L and this infinity, they are not the same. So because the limit of this is L and the limit of that is positive infinity, and they are different, then we say that the limit as x approaches a of f of x does not exist, right? It does not exist. But look into this now. I did not want to talk about this because we already understood how this thing works, that if the limits are not equal, the limit on the left and on the right, one-sided limit or left-hand limit and the right-hand limit, if they are not equal, then the limit does not exist. I want us to talk about this value a here. Now, what I wanted to talk about a. Is a now an asymptote? I mean, this function at this point is actually defined, because if I'm looking into this function is defined here. But if I'm looking into this function here, as I get closer and closer and closer and closer, it's not going to touch this. Now the question is, are we actually having an asymptote here? What is an asymptote? An asymptote is actually it's actually a nice value here, such that this function is actually not being touched when we are considering a certain portion of it. So if you look into this now, because this function here, this piece of this function, because this function will be defined like this in one piece and also defined like this in another piece. If you look into this function here, as it gets closer and closer to this value on the right, then you can see that this function is not going to touch this. Even though on the left is touching, but on the right is not touching it. So this one, at A, we are actually having a vertical asymptote. Right. It doesn't really matter that this piece here is touching there. What is important is that we have this piece here that is going and is not touching that value. So A is also asymptotic. So based on this piece, there is an asymptote at A. So when do we usually have a vertical asymptote? Whenever you have a vertical asymptote, you must know that one of the following things happened. So if you find out that the limit as x approaches a of f of x, you are getting positive infinity, you must know that at x is equal to a, there is a vertical asymptote. If whenever you take the limit as x approaches a of f of x and you are getting a negative infinity, you must know that at x is equal to a, you have a vertical asymptote. If you happen to have the limit as x approaches a on the right of f of x, you must know equal to, let's say, positive infinity, right? Let's say you are getting positive infinity. You must know that at x is equal to a, once you have this happening, that when you are taking a value so close to a on the right, you plug it here, you're getting a positive infinity. Rest assured that actually this function have an asymptote at x is equal to a. If whenever you are taking the limit as x approaches a on the left of f of x, you are getting a positive infinity, then just know that there is a vertical asymptote at x is equal to a. And if it happens that when you're taking the limit as x approaches a on the right of f of x, you are getting a negative infinity, you must know that there is a vertical asymptote at x is equal to a. If when you are taking the limit as x approaches a on the left of f of x, you are getting a negative infinity, just know that there is a vertical asymptote at x is equal to a. Look into this. If either this happens, then there is a vertical asymptote. If or this happens, but that is not happening, as long as one of these things happens, then you must know that you have a vertical asymptote. That's actually how we know that there is a vertical asymptote or there is no vertical asymptote. Looking into this part here, we only have this part satisfied. This one is actually saying that on the right we are getting to positive infinity, which means that actually a is an asymptote. So to know something is an asymptote, it must obey one of these or all of them. Because if it obeys this, then it obeys this one and that one at the same time. If it obeys this, then it obeys this one and that one at the same time. Or if it obeys this one, then it obeys this one, but still we have a vertical asymptote. So that's what this lesson is all about, vertical asymptotes. Now, how do we know that we have a vertical asymptote if you are actually given a function? How do we know? So that's the question that we have. How do we know that we have a vertical asymptote given the function f of x? How do we know? Now, remember that here we're talking about the case. If it happens that you have a plot like this, either this or that or that or this one, you know that you have a vertical asymptote. But not every time we give you a plot, sometimes we just give you a function. If let's say we're talking about 0 over 0, we know that you actually end up having a nice thing like this one here. So you have a hole, because when you're plugging in here you get a 0 over 0. If you have a hole, you know that you are coming from a function that actually when it was evaluated you're getting a 0 over 0. That was it. Now I want us to take some examples here and see if we can conquer them. So the first one is just saying evaluate. We usually use evaluate or find. Of course you will know the wording that will be asked, that actually they want the value of this limit. Evaluate the following limits. First one is find the limit as x approaches 0 of 1 over x. Second one, find the limit as x approaches 0 of 1 over x squared. Third one, find the limit as x approaches 1 of x minus divided by x cubed minus x. And then the fourth one, find the limit as x approaches 3 of x plus 2 divided by x minus a 3. Like I said, the main goal of actually this particular course, we wanted to analyze the function fully until we can tell everything about this function. Of course, if you were to, let's say, continue with maths, we're going to use that understanding into if let's say now you wanted to predict if you are given certain points, you want to use that information to actually analyze maybe a certain data. You get what I mean? But for now, let's just analyze the function as it is and see what we can actually get out of these functions. Okay, always the first thing when we're saying evaluate, take this value here and plug it in the value of x. So if we are plugging in here, we will get 1 over 0. That's what I want you to notice here. Whenever you are getting a number over 0. The reason I'm saying a number here, I'm talking about a number that is not 0. I'm getting maybe 5 or 6, but this number is not 0, because if you are having a 0 over 0, you know what to do. But I'm talking about a number divided by a 0, right? In this particular case here, if I'm plugging in a 0, I'll get 1 over 0, right? Which is a number. This is a number which is not 0. Now, if you are getting a number over 0, you must know that at that particular point x, you have a vertical asymptote. It's a vertical asymptote if you have this. Now, how do you deal with that? The first thing that you do after plugging in, you just draw a Cartesian plane. That's not hard. It's not hard at all. Cartesian plane. Simple like this. Very, 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 very simple. Don't make it hard. The second thing that you do, you draw a vertical asymptote at x equal to this number here, which is 0 in this particular case. So the vertical asymptote will be, let me use a red so that we can see. There is a vertical asymptote at x is equal to 0, which is along the y-axis. These are x-axis, these are y-axis. Now, after you have drawn the Cartesian plane and you have drawn the vertical asymptote at x equal to this value, the next thing that you need to do, remember that here we have a 0. You pick a value so close to 0 such that the computer and the calculator is not going to figure out what just happened here. And then you plug that value here in this function. So if let's say here, let's say the value that I'm going to pick here is going to be 0,000000001. Right. How many zeros did I pick? 1, 2, 3, 4, 5, 6, 7, 8, 9. I have 9 zeros, which means there are 10 numbers after the comma. So if let's say I were to plug in here that number, I would end up having 1 divided by 0,000000001, right? To remove all these zeros, I have to multiply by, because there are 10 numbers here, so I need to move a comma 10 times. So I'm going to multiply by 10 raised to 10. Because this 10 raised to 10 here was not there, I have to multiply the numerator also. Once I multiply this, is going to move a comma to this point. So in the denominator, I'll end up having a 1. But in the numerator, I'll get 10 to the power 10. A very, very, very big number. What is important about this whole thing? You don't really have to get the number at all. If I pick a value that is so close to 0 and I plug it here, as long as I'm picking that value on the right of 0, I will get a positive number. What I want you to know here is that once you get a positive number, the function is actually going like this as we are getting closer. So it's going all the way up. It's not going to touch the y-axis. If I pick a different value, let's say on the left, negative 0,0000001, I plug it here. I don't really need to know the value. I don't care about the value. What I care about, once I plug that value here, am I going to get a positive or a negative value? So if I plug it here, I will end up getting a negative value, because 1 divided by something negative, because when I'm picking a value on the left of 0, it's going to be negative either way. So I will end up having a negative. A negative is saying this function, as we are getting closer to 0, it keeps going all the way down, but it's not going to touch the y-axis. What does that supposed to mean? When I'm taking the limit as x approaches 0 on the left of 1 over x, what I'm going to get, I'm going to get negative infinity. So this is going all the way down. When I'm actually taking the limit as x approaches 0 on the right, of 1 over x, I am actually getting positive infinity. That's all there is to this. You are actually checking the sign. If I pick a value so close here and I plug it there, will I get a positive or negative? If positive, it means you're going up. If I pick a negative, a value on the left of 0, I plug it there, what will I get, a positive or negative? Of course, if I'm plugging a negative here, I will end up having a negative. That's why we are going to negative infinity. Again, the first thing that you do, first plug in. If you are getting 0 over 0, all you need to do, one, you can factorize or rationalize. There are two other methods which we haven't yet done. If it happens that when you're plugging in, you're getting a number over 0, this is the only thing that you need to know. You don't have to plot this whole function. You can if you know, because we know how to plot this part. What is important here is that we just wanted to know what is happening close to 0. That's why the limit. All right. Let's try now this one here. The first thing that you do, you take 0, you plug it here. So I'll end up having 1 divided by 0 squared, which is 0. So we are falling into this case. First thing that you do, you draw a Cartesian plane, just like that, just to see what is happening close to the value x, which is 0 in this particular case. And then this value here, which is 0, we wanted to actually do realize that it is an asymptote, because we're getting a number over 0, so there is an asymptote at that point. Now, if you're still here, this is 0, I pick a value on the right of 0, just close to 0, I plug it there. Note that a value on the right of 0 is positive. I plug in a positive value, I square it up, I will still gonna get a positive value. So positive number, because 1 is positive divided by positive, I'm going to get a positive. So this function on the right is going this way, smoothly like that. If I pick a value on the left of 0, I plug it here. This value that is on the left of 0 is negative. Taking a negative thing, you square it up, you get a positive thing. Positive divided by positive is still positive. So this function here on this side also, it is also going up. So the limit as x approaches 0 on the right of 1 over x squared is just going to be positive, this positive infinity. And the limit as x approaches 0 on the left of 1 over x squared is just going to be, because it's still going up, so it's still positive, so you still get a positive infinity. So the limit as x approaches 0 of 1 over x squared is going to be, because positive infinity and positive infinity, you're still gonna have positive infinity. In this particular case here, because this one was positive infinity, negative infinity, this one was positive infinity, so we were going to say that the limit as x approaches 0 of 1 over x does not exist. So that's what we're going to say in this particular case. But here it is actually positive infinity. Now, I want us to look into this one also here. I want us to look into this one. If you look into this this particular case here, we are actually having okay, we don't usually just jump and plot. The first thing that we need to check, are we getting a number over 0? Okay, so if let's say I take 1 and I plug it here, right, I take 1 and I plug it here, what will I end up with? I will end up with 1 here divided by 1 cube is 1 minus 1, which is 0. So I will have 1 over 0, right, which is a number over 0. Now, someone might be thinking that I have an x and x and x, I need to cancel it out, blah, 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 blah. You don't really have to do that. You don't really have to. But just for you, if you really wanted to do it, we can just say this is going to be equal to the limit as x approaches 1 of, if we're factorizing this, I mean, it's still going to be that x. If we're factorizing this, I will have x outside. Inside, I will have x squared minus 1. And of course, this is going to be the same as the limit as x approaches 1 of this x, and that x will cancel out, and now you'll be left with 1 over x plus 1 and x minus 1. I'm trying to factorize this here. Now that you have this nice thing here, then you know that when I'm plugging in 1 here, I will end up having a 2. When I'm plugging in a 1 here, I will end up having a 0. 0 times 2 is 0, so I will end up having 1 over 0. Now, how do we deal with a number over 0? You just need to plot the damn thing. So we plot this like this, nicely like this. So if you're plotting this, what is the next thing you do? Of course, the next thing you do, you're gonna have a y and an x here. After you have done that, you look at this. Oh no, we're here. You look into this value here. X is equal to 1. So since x is equal to 1 here, what we need to do here, we just need to go at x is equal to 1. 1 is somewhere there, and then we place a vertical asymptote at that point. My plot is not that perfect, guys. Yeah, so we plot a vertical asymptote around that point. Now that you have that plot there, that asymptote there, what do you need to do? To solve a limit, all you need to do, pick a value so close to 1 first, just on the right of 1. So I am going to pick a value here which is on the right of 1 here. All right, if I were to pick a value on the right of 1, remember that the value that is just on the right of 1 is bigger than 1. But when we're picking that value, we pick it so that we pick it so close to 1 so that even this calculator is not going to figure out what we did, but we know what we are actually doing here. So if I pick a value so close to 1, the calculator is not going to find out. We're not going to tell it that it's bigger than 1. We're just going to cheat it out, which means that around this point, that point, even though the calculator cannot pick it out, we know that if it's on the right of 1, it's going to be bigger than 1. So if I am plugging in a value bigger than 1 here, and I'm adding a 1 to it, I will get a value bigger than 2, which is positive. If I am plugging a value bigger than 1 here, and then I'm subtracting a 1 from it, I will get a value positive, of course. Let me repeat it. If I pick a value on the right, it's bigger than 1. So subtracting 1 from it, I will still get a number which is 0,000 something, because that number is bigger than 1. It's closer to 0, but it's still bigger than 0, so it's positive. This is this part. But if I'm plugging in here very bigger than 1, I will get something positive because I'm still adding. It was positive, so I'm still adding. So positive times positive will give me a positive, and then 1 is positive, so I'll end up having a positive divided by positive, and then I end up with a positive number. That's what is important here. Positive number means we are going all the way like this up, but it's not going to touch the asymptote. That's what is important. If I pick a value here so close to 1, such that the calculator cannot figure it out, fine. What we know is that a value that is close to 1, it is bigger than 0, so it is positive. So that value, because it's positive, when I'm actually adding a positive value to a positive value, I will end up with a positive times. If I pick a value on the left of 1, that value is less than 1. Yes, the calculator is not going to figure it out. The computer is not going to figure it out. But it is still, we know that value, because on the left, it must be less than 1. Because that value is less than 1, when I'm going to plug it here, remember. I'm going to subtract 1 from it. When I'm actually subtracting a bigger number from a smaller number, I end up with a negative. So from this side, I get a negative. So when I'm getting a negative, right, this is going to be negative. Positive times negative is negative. I'm dividing 1, which was positive. Positive divided by negative, I get a negative. So having a negative means we're going down. So the function is going like this, close to 1, but it's not going to touch the asymptote. So in this particular case here, we have the limit as x approaches 1 on the left of x divided by x cube minus x is equal to negative infinity. And when you're looking at the limit as x approaches 1 on the right of x divided by x cube minus x is equal to positive infinity. So we have positive and negative, which means that the limit as x approaches 1 of x divided by x cube minus x is actually, we can say that, does not exist. That's what is important here. Of course, I was trying to adopt or use the factorization methods. When you are plugging in 1 here and you end up having 1 and then you will end up having 0 in the denominator, you don't really have to factorize, but this is just one of the easiest things that we can do. You don't really have to factorize. You can get all this information from actually this original equation. So technically speaking, you don't really have to do this, especially once you know that you are actually getting a number over 0, but you still follow the same thing of just plot a curve, show that actually when I'm picking a value somewhere there, I will end up getting, and take that value and plug it there, I will end up with a positive value. And when I'm picking a value here and plugging it there, I'm gonna get a negative value and then go all the way down. Of course, different examiners prefer different things, but literally speaking, there's not much needed to factorize blah 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 to get this, because this you can get it from there if you are getting this or not. Now let's look at number 4. If I were to plug in 3 here, I will get 3 plus 2, which is going to be 5, and then plug in 3 here, I will end up 3 minus 3, I will get a 0. 5 is a number that is not equal to 0, so there is only one method that we have to try out, right? And it's going to tell us the whole story. So what is the method is saying? Plot the Cartesian plane. Plot the Cartesian plane. When you're plotting a Cartesian plane, make sure that you have the y-axis and the x-axis. After that, you go to this value here, x is equal to 3. When x is equal to 3 here, you draw a vertical asymptote at that value. Once you draw a vertical asymptote, everyone should be happy now, because all you need to do, you just need to pick a value just on the right of 3. If I pick a value just on the right of 3, that value can be 3,000000000. It doesn't matter how many zeros, I'll place a 1 in the end. Now, if I take this value here and I plug it here, I will end up having 3,0000000 plus 2, which means we will end up having 5,0000001, which is positive. So we'll end up with positive in the numerator. In the denominator, if I'm plugging 3,000 something, and then I'm subtracting a 3, this 3 here will be gone and you'll be left with 0,000 something, but it's still going to be positive. In matter of fact, what is important is that 3 comma something is going to be bigger than this 3. So when I'm separating something smaller from a bigger thing, I get a positive thing. So here I will have a positive. Positive divided by positive, it is actually a positive. So in this part here, we have a positive, which means we're going all the way up. Positive means we're going up. And also the limit as x approaches 3, this point here is on the right, which means on the right we always place a plus of x plus 2 all over x minus 3 must be going to positive infinity. So we have positive infinity. Now if I pick a value on the left of 3, so I pick a value there and I plug it here, a value close to 3 is positive, so that value plus 2, I'm still gonna get a positive thing as here. And then if I am taking a value just on the left of 3, which is going to be 2,9999999, right, and then I plug it here, that value is always going to be less than, because a value on the number line or on the x-axis that is on the left of 3 is less than 3. So subtracting from a smaller number, so I'm subtracting 3 from a smaller number, I will get a negative answer. So I will get a negative. Positive divided by negative is negative. So this side I have a negative, which means our function is actually going all the way down. So in this particular case here, we'll end up saying that we are actually having the limit as x approaches 3 on the left of this particular function here divided by x minus 3. This must be equal to negative infinity. Hence we say that the limit as x approaches 3 of x plus a 2 divided by x minus 3 does not exist. That's what is important here. That's all. Just a quick recap. First you plug in. Once you plug in here, if you are getting a number over 0, you draw a Cartesian plane, and then at x is equal to that value there, that's when you draw an asymptote, and then you pick a value on the right, you plug it in and see if you are getting a positive or a negative. If you are getting a positive, which means the function as you're getting closer to that function is actually going to positive infinity, and then you pick a value on the left. If it is positive, then you're going to positive infinity, then your limit will actually go to positive infinity. Otherwise, you can either have one going up and the other going down. In that particular case, you actually having a limit does not exist, right? Limit does not exist. Another thing that I want us to look at here, let's just take one last more example here. Suppose I want you to evaluate the limit as x approaches, let me say it approaches 1, and then in the numerator we'll end up having minus e to the power x all over, I'm going to end up having x minus 1, and then I'm going to square it up. What will be the limit of this? The first thing that you actually do, you plug it in. If you are plugging in here, you will end up having minus e to the power 1, or just e, and then in the denominator we'll end up having 1 minus 1 squared, which is minus e divided by 1 minus 1 is 0, 0 squared is 0. What is important here is that this value here is the number that is not equal to 0. That's what is important. So we are getting a number over 0. So of course, even in this particular case, all you need to do is to just draw a Cartesian plane, and then after that you draw a vertical asymptote at this value here when x is equal to 1. So we'll end up having a 1 here. You draw a vertical asymptote, And then once you get there, you choose a value on the right, you plug it in there. So if I'm plugging a value here on the right of 1, I'm going to plug it here. I will still going to get e raised to 1, which is a positive number, times a negative. I'll get a negative. In the numerator, I'll get a negative. And then if I'm plugging a value on the right of 1, that value minus 1 squared, I will end up having a positive in the denominator. What is important here is that I have this. If the number is on the right of 1, that number is bigger than 1. So subtracting 1 from a number bigger than 1, I'll get a positive. Squaring a positive number, I get a positive. That's what is important. Plugging in a 1 here, e to the power s is always increasing. Once you place a minus, which means it's always going to be decreasing, right? So this one, whatever the value that I'm going to plug here, e to the power x is going to be positive, but because of this number, it's always going to be negative. So a negative divided by positive is going to be negative, which means the function here is going down. So the limit as x approaches 1 on the right of minus e to the power x divided by x minus 1 squared is equal to negative infinity. And then if I pick a value on the left and then I plug it here, a value on the left, it doesn't matter. Even if it was here, we know that an exponential function e to the power x is like this. So I have y is equal to e to the power x. So all the outputs that we have are saying that this is always bigger than 0. Now, when I'm saying I have y is equal to minus e to the power x, it's actually the reflection along the x-axis. So the function will start to look something like this, right? So this one is y is equal to minus e to the power x. So if you look into this function here, it's always going to give you negative values. So this one here, whatever the value of x I'm going to pick, the output is always negative. So I will get a negative. But if you look into this one here, we know that function, the function y is equal to x squared. So it looks like this. So once I'm having x minus 1 squared, which means I am shifting this curve to the right. So I'm going to shift it like this. So this one also is going to be positive. For this one is always going to be positive. So having a negative over positive, it means that this side also I'm going to have a negative, so you can go all the way down. So the limit as x approaches 1 on the left of e to the power x minus divided by x minus 1 squared is equal to negative infinity, and which means now this limit actually is evaluating to negative infinity. So either way, you can analyze this either as functions or you can just plug in a value. So if I'm plugging in a value here, e to the power x is going to be positive number. It's going to be e raised to 0, e raised to 1,0000001, but it's still going to be a positive number. Multiply by a negative, you get a negative, and then you come here, plugging in a value bigger than 1, I'm going to get a positive thing. Raising it to an exponent, I'm going to get still a positive thing. So I get a positive over a negative over a positive, which means that I have a negative this side. And also you do the same here. When I pick a value here, I plug it here, I will get 0,99999. So e is going to be e to the power 0,9999, and then you multiply by minus here, so the answer you'll get is going to be negative. And then here, when I'm plugging in 0, something, so it's less than 1, I will get a negative inside, and then I square it up, I'm still going to get a positive. So I'm still going to have a negative over a positive, which means that it's negative. So we're going all the way up, down, I mean. So that's what is important about this whole lesson. Hopefully you enjoyed it. If not, it's not the end of the world. We can always try other ways of doing this nice thing here. Thank you very much for this particular lesson. Hopefully you will still be having enough energy when we're actually dealing with the rules for limits. We're gonna just deal with them as quick as possible, because most of the time actually needs to be spent around the squeeze theorem, because most of these rules that we actually deal with when it comes to rules of limits, in simple words, it's just plugging in. So if you noticed here, the first thing that we say, plugging in, plug it in and see what you're getting. So in most cases, you'll find out that when you're plugging in, you are actually starting to actually evaluate the limit. That's what we actually do. So some of these rules will actually be around the plugging in. That is why most of the time we usually get faster and faster when we are dealing with rules for limits, is because that's what we've been doing, plugging in. But of course, mathematics needs to happen and be explained, so we'll go through that.